All right, next we want to talk about the natural logarithmic function and how it relates to integration. So first off, let's just talk about the natural log function. And we're going to start off with this question. Find an antiderivative of the function using the power rule for integration. So here we have the indefinite integral of 1 over x dx. So first thing we would want to do is change this to our negative exponent. So this is x to the negative 1 dx. And now if we're going to use our power rule, remember this is x to the n plus 1 over n plus 1. So if we add 1 to negative 1, we get a 0. And then we divide by that n plus 1, so we divide by 0. And anything to the 0 power is 1, so this becomes 1 over 0. And you can see that this is going to be undefined. Okay, so if we're looking at the general power rule, the indefinite integral of x to the nth power is x to the n plus 1 over n plus 1 plus c, as long as n does not equal negative 1. Okay, because if n is negative 1, then the general power rule is undefined. So the answer to this question is neither algebraic nor trigonometric. And just because we get an undefined answer doesn't mean there isn't an answer. And in math, a lot of times when we get something that's undefined, we create new math to describe what's happening. So we need another class of functions to describe this integral. Here enters the natural logarithmic function. Okay, now we know that this integral must exist because here is the graph of 1 over x, right? And if we just took any integral, so this would be like the integral from 1 to 2, you can see that this indeed does have an area. So it just doesn't mean that this is undefined. There is an answer to it. It just is not going to be found using the power rule. So if we were to think about the natural log function and we wanted to find its derivative, so remember the derivative with respect to x of ln of x equals 1 over x. And if I wanted to find the integral here, remember we can use the second fundamental theorem of calculus because the derivative of the integral is just the inside. And so we would see this sort of cancellation here of the derivative of the integral, leaving us with just the natural log of x. Okay, and so this actually gives us the definition of the natural logarithmic function. So ln of x equals the definite integral from 1 to x of 1 over t dt. And here x has to be greater than 0, so it doesn't make sense for the natural log function to be less than 0 here. So instead of using the power rule here, the antiderivative of 1 over x is actually just the natural log of x. All right, next we want to talk about the log rule for integration and actually integrate some of these here. So it says let u be a differentiable function of x. And it says the integral of 1 over u du equals the natural log of the absolute value of u plus c. Notice it has to be absolute value because we can't take the natural log of a negative number. Or alternatively, we can also think of this as u prime over u dx. So this integral is the natural log of the absolute value of u plus c. So again, we're just kind of undoing that thought. Remember, if we take the derivative with respect to x of the natural log of u, that was u prime over u. And so now we're just going backwards. Okay, so if we take this integral, this is kind of what we get right here. Okay, so we want to use the log rule for integration in this function right here. And first thing we want to do is take out that constant multiple. So we'll rewrite this as 2 times the integral of 1 over x dx. And this is the most simple form. So here the integral of 1 over x dx is the natural log. So this is going to be 2 times the natural log of the absolute value of x plus c. Okay, so this case came out nice and perfect to the 1 over x. Now the trick is going to be recognizing quotient forms of the log rule. Okay, in other words, what we're looking for is u prime over u. That's going to be our ticket. So looking at this, we want to see what can we let u equal. So a lot of times, just try to let the denominator equal u. So if we do that here, we get x cubed plus x. And then let's go ahead and find u prime, which would be 3x squared plus 1 dx. Okay, and let's see if we can find u prime over u in this form. Here, I would see my u prime. So here we have the integral of u prime over u. And so we can go straight to the natural log of the absolute value of u plus c, and then substitute u back in. So this really equals the natural log of the absolute value of x cubed plus x plus c. Okay, so for letter B here, we're going to let u equal tan x, and we know u prime is secant squared x, and so you should be able to see here u prime over u. And so this then becomes the natural log of the absolute value of tan x plus c. All right, in example C here, we're going to let u equal x squared plus 2x, following with the denominator there, and u prime would be 2x plus 2. And if we look, we only have an x plus 1 on top, so we don't quite have u prime, but if we multiplied the numerator by 2, then we would have our 2x plus 2. And to keep this balanced then, we have to multiply on the outside by 1/2. Okay, so we really have 1/2 times the integral, and we'll distribute that 2 to get 2x plus 2 over x squared plus 2x dx. Now we have u prime over u, and so our final answer is going to be 1/2 times the natural log of the absolute value of x squared plus 2x plus c. All right, for letter D, one more example here. So u we're going to let equal 3x plus 2, and u prime is going to equal 3. Notice we don't have a 3, so we need to multiply by 3 on the inside and 1/3 on the outside. So our final answer is going to be 1/3 times the natural log of the absolute value of 3x plus 2 plus c. All right, next we want to look at an example of using the log rule with a change of variables. And if you'll notice in letter A, this is very much the same as what we just did here in the previous example. So if u had been 4x minus 1, u prime would have been 4, and notice we're missing the 4, so we'll add on the inside and put a 1/4 on the outside. And so we simply go straight to 1/4 natural log, the absolute value of 4x minus 1 plus c.
All right, in our next example, you'll notice the rational expression here, and the degree of the denominator is a 2 and the degree of the numerator is a 1. So this is a good candidate for using the log rule. So let's try change of variables. We're going to let u equal the denominator, 5x squared plus 1, and then we'll find du. And so the derivative of 5x squared plus 1 is going to be 10x, and don't forget the dx part. Now we're going to go ahead and solve for dx, and to do that, divide by 10x. And so we get dx is equal to du over 10x. Now we can go ahead and do substitution, and we're trying to get rid of all the x values. Well, the 2x we're just going to leave. The 5x squared plus 1 we're going to leave as u, and then we're going to rewrite dx as du over 10x. What you're going to notice from here is that this x divided by x will cancel out, and then the 2 over 10 will also become 1 over 5. And you can pull the 1 over 5 out in front of the integral sign, and then we have 1 over u du. All right, well, this is exactly our rule, so we're going to keep the 1 over 5, and the antiderivative of 1 over u du is going to be the natural log, absolute value of u. and then plus c. And then what we're going to do is go ahead and just back substitute for u, which was right here, 5x squared plus 1. So we have 1/5 natural log absolute value of 5x squared plus 1, and then plus c. Now because u is actually always positive, because x squared is positive, and then plus 1 keeps it positive, we don't have to use the absolute value symbol here. We can actually just write 5x squared plus 1 in parentheses. And here is your final answer.
Next, we want to do an example where we need to use long division before integrating. So here, if we look at the u and du, if we let the bottom just be u, the du would be 2x. And you see we have an extra x squared here, so it's going to be a little weird. So a lot of times we want to actually try to divide this before we integrate. Okay, so let's use long division here. So we're going to have x squared plus x plus 1 divided by x squared plus 1. And so x squared goes into x squared one time. Okay, so if we do 1 times x squared plus 1, we get x squared. And then if we line it up, the 1 would go right here. And then remember, we have to subtract this. And so I want to change all of the signs. And when I change signs, I circle it so that I know that I actually changed the sign. And let's subtract here. So x squared minus x squared, you get 0. X, you have nothing to do there, so you just bring down your x. And then 1 minus 1 is also 0. So all you're left with now is x. And so x squared doesn't go into x anymore, so all you have to do is go plus the x divided by x squared plus 1. Okay, so you still have x divided by x squared plus 1. And so let's rewrite this integral now as the integral of 1 plus x over x squared plus 1 dx. Okay, and let's separate these into two integrals here. So the integral of 1 dx plus the integral of x over x squared plus 1 dx. And now if you look here, we can let u equal x squared plus 1, and u prime would be 2x. So we have u prime over u if we had a 2 here and a 1/2 here. Okay, so now we can go ahead and integrate all this. The integral of 1 dx is just x. And then here we're going to have 1/2, and then this is u prime over u. So it's the natural log of the absolute value of x squared plus 1 plus c. Now one note here. Since this is x squared plus 1, can x squared plus 1 ever be less than 0? Okay, so this is a question. Can x squared plus 1 ever be less than 0? Well, the answer is no. There's actually no real roots. So what we do here, instead of having the absolute value sign, is we change it to parentheses. Okay, because this cannot happen. So instead of having absolute value here, you're just going to see this in parentheses. So in J here, you can see that we do have a power of 1. Okay, so we can't just use our power rule. Now again, what we always want to do is divide this out first. So this is the integral of x cubed over x plus 2x over x plus 1 over x dx. So go ahead and divide that out first, and then you can simplify. So this is really the integral of x squared, because x cubed over x. And we'll split this into separate integrals. And then 2x over x is just going to be 2. And then plus the integral of 1 over x dx. And then we integrate each one separately. So here we get x cubed over 3. And then this one becomes 2x. And this last one becomes the natural log of the absolute value of x. And finally plus c. So divide out first if you can. Alright, in our next example we want to evaluate a definite integral. So here's our definite integral from 0 to 3 of x over x squared plus 1. So again, we're still going to do the same u, let that be x squared plus 1, and du is going to be 2x dx. And so you can see we're missing a 2 here, so we'll add a 1/2 on the outside. And let's go ahead and integrate this. So we have 1/2 times the natural log of the absolute value. Well, we don't even need absolute value anymore because it's x squared plus 1. And we want to evaluate this from 0 to 3. Okay, so now we're going to apply the fundamental theorem of calculus here. So we're going to get 1/2, and we can actually factor this outside, times the natural log, and we'll substitute in 3, so 3 squared plus 1. And then we're going to substitute 0, so the natural log of 0 squared plus 1. And so this is 1/2 times the natural log of 10 minus the natural log of 1. Okay, and we know that the natural log of 1, remember, it's going to be from 1 to 1, and so this actually equals 0 here. So we're left with 1/2 times the natural log of 10, and remember the exponent can come up here, so this is really natural log of 10 to the 1/2, which is the natural log of the square root of 10. And either way, if you put this into your calculator, you're going to get about 1.151. Okay, so that's how we're going to evaluate our definite integrals using natural logs.